I'm Nick Hutzler. I'm from Caltech, and I'm excited to tell you about searches for fundamental symmetry violations with atoms and molecules. There we go. To introduce myself, I'm a physics professor at Caltech, been there for a few years now. My expertise is atomic molecular optical physics, or AMO physics, and I'm an experimentalist. What I work on has an emphasis on precision measurements of fundamental physics, sort of like high energy nuclear physics of the type that I'll talk about, using molecular systems. After mid-March of 2020 or so, my group started doing some theory dabbling as well for various reasons. My research background, I worked as an undergrad, I worked on a neutron EDM experiment. For grad school, I worked on an experiment that I'll talk about today, on an electron EDM experiment called ACME. And then for my postdoc research, I did laser cooling and tweezer trapping. So none of these things are high energy physics. I'm not a particle physicist. So it's exciting to be here at particle physics science school, hopefully a summer school, and hopefully I don't make a fool out of myself. So for the content, I will mostly focus on CP violation searches in atoms and molecules. Mainly because this is what I do and what I know, and hopefully what I can give an interesting perspective and background on. But the ideas and techniques that I'll talk about are very widely applicable. So I'm going to try to talk about things that are that you'll probably hear about in other areas as well, like other high energy physics areas, quantum information science, chemistry, fundamental chemistry. And yeah, just to remind you, I'm an AMO experimentalist, so I'll especially gloss over some of the high energy stuff. This is not a review, so it's not comprehensive. I have some reviews to suggest if you're interested, and please feel free to get in touch anytime, including raising your hand or emailing me. And I would also like to echo Mariana's suggestion that you ask a lot of questions. If you'd like to see the slides, you're going to download them so that you can annotate them or something. I'll put them on the website, like the Trisep site, but for now, if you go to my group website, which is hutzlerlab.com, go to teaching, and then there's something Trisep 2022, so you can download them there. I would have uploaded them to the website, but I'll be honest with you, I was still working on them up until 30 minutes ago. So.
I'll upload them for you.
Thank you.
And did you say you want to record?
Yeah, and I already hit it, so
okay.
Yeah.
Okay, good.
Great. So yeah, so feel free to pull those up if you're interested. So I want to focus on the things that I'm going to talk about in this lecture. Understanding the motivation to search for fundamental symmetry violations. That will mostly just be sort of a recap and a connection to some things that I'm talking about, because I'm not the first person who talked about like the baryonic symmetry of the universe, nor will I be the last probably. What I want to do is focus more on like what makes atoms and molecules sensitive to fundamental symmetry violations. So focus on intuition and understanding, and exploring the different manifestations of symmetry violations in these systems. And I will talk about experiments. I'm an experimentalist after all, but I'm mostly going to use them. I'm not going to sort of talk about all the different features and details, but I'm going to use them as a vehicle to explain the concepts and the methods. And also with an eye to the future. What's going on now, or what things are going to be going on, hopefully that you'll hear about in your scientific careers. So the first part, background and motivation. Why are we interested in CP violation at low energy, and how are atoms and molecules used for these searches? But before I get started, are there any questions so far? All right. So I will go through this part fairly quickly. As you know, there's a large imbalance between matter and antimatter in the universe. This is called the baryonic symmetry problem. How can we explain this? One way would be some undiscovered particles, say which was created after the Big Bang, and preferentially decays into matter. So thus, on average, turning energy into some net balance of matter, not antimatter. One can show, as Sakharov did, that you need, in order for this model to work, you need three conditions. You need baryon number violating processes, you need departure from thermal equilibrium, and you need C and CP violating physics. And this is what I won't say anything more about these. I'll talk about this because this is what's relevant to the science that I'll be talking about. The reason why you need C violation, charge conjugation violation, is fairly straightforward to understand. If all the laws of the universe were symmetric under charge conjugation, then if you had a process like this which generated a net matter imbalance, you would have necessarily at the same rate the charge conjugated process happening, and then you get on average no net asymmetry between matter and antimatter. So okay, that's why you need C violation. You know, why CP? From this particle physics picture, it's mostly just sort of a technicality, but it ends up having really important consequences. If you violate C but preserve CP, then the charge conjugated and mirror inverted process will happen at the same rate. So these would happen at the same rate, and you would still not get a net matter imbalance. So you need C and CP to be violated for this to happen. And the CP part is especially interesting, at least in my opinion, because it shows up in a lot of other places at high and low energies. You know, there's reading here about CP violation a lot because it's very interesting. And the reason I'm interested in it is because this new CP violating physics, as long as it couples to this standard model, generically gives rise to electromagnetic moments in regular standard model objects. Those moments, which I'll talk about all of them, are electric dipole moments in fundamental particles and in composite particles like nuclei, higher order moments called nuclear shift moments and magnetic quadrupole moments. There are also more, but these are the sort of ones you hear about the most. The reason that this is a problem, the sort of one-line proof, which I will explain in a little more detail, why the very existence of these moments is some symmetry violating problem, is because if you have say a particle like an electron or even a composite particle like a neutron, it has an intrinsic spin. If it also has an electric dipole moment, it has to lie along the spin because that's the only internal vector that describes particles, and dipole moment is a vector object. And so that means the dipole and the spin have to be parallel to each other or anti-parallel. They have to be aligned to each other. And that's a problem because dipole moment is a parity odd time reversal even quantity. Spin is a parity even time reversal odd quantity. So these two things can only be the very existence of these two things in the same object being parallel or anti-parallel violates a number of fundamental symmetries: parity symmetry, time reversal symmetry. So there's so that's the proof, that's the math proof. But there's a nice intuitive way to understand this, which is how I like to think about it. So here's your particle with your dipole moment and a spin. Of course, it's a very classical picture because an electron is not actually like a charged sphere, it's a point particle, but the classical intuition is completely valid here. If you look at this particle in a mirror, it would be spinning in the same direction. The mirror image would be spinning in the same direction, and the mirror image of something spinning is spinning with the same sense. But the dipole moment would flip. That's coming from some spatial degrees of freedom. And that's interesting because this particle does not exist. Right? If this is what the electron looks like, then the electron does not look like this. These two particles would be physically distinguishable. I could apply like electric magnetic fields and tell you like, did you give me this type of electron or that type of electron? But there's only one type of electron. All electrons are indistinguishable. We know that from the Pauli exclusion principle in quantum statistics and atomic spectra, that there's only one type of electron. So if the electron, same with neutrons, protons, if they have an intrinsic permanent dipole moment, that very existence of that moment violates parity symmetry. And similarly, time reversal symmetry. So, if you look at this particle spinning and you apply time reversal, now it's spinning in the other direction, but the charge displacement doesn't care. That particle also doesn't exist. So the very existence of electric dipole moments violates parity reversal, time reversal, and CP if you assume that CPT is a good symmetry, which I think people usually do. Any questions about this?
I'm not entirely sure, like I don't understand the argument why spin and dipole have to align or why.
Yeah, great question. So why do these have to align? So spin is the only intrinsic, so the dipole moment would be some intrinsic property of the particle, like a rest frame property of the particle. And it's a vector. And we know that there is an internal vector describing, particles, electrons and neutrons, which is the spin. And we also know that there aren't any others. There are no other internal degrees of freedom, say of an electron. And the reason we know that is because you can only put 2 electrons in like the same s orbital. Right? You can put spin up and spin down. If there was some other internal degree of freedom, you could have spin up, spin down, other thing up, other thing down. So you could have like 4. So we know that we know from quantum statistics and like atomic structure that all electrons are indistinguishable and that they only have this one internal degree of freedom, which is a vector, which is spin. So if the electron has some other vector, intrinsic vector, it has to be aligned with the spin. It can't be independent from the spin. It has to be, determined fully by it. So for those reasons, or any other vector quantity you could cook up that was intrinsic to the electron, it would have to be parallel to the spin, parallel or anti-parallel. So that's why, and then that's why there's this problem. I saw it looked like there was a question in the chat.
So QED violates CP. So the question is, does QED violate CP?
No. QED does not violate CP. At least the only physics you know about that violate CP is the CKM matrix. QED does not violate CP.
I guess the point is to get an EDM, you need something beyond QED.
Exactly. Yeah. If you calculated what is the dipole moment of the electron in QED, it would be 0. It'd be exactly 0, and that's because you can't construct any Feynman diagrams that have CP or T asymmetry. I'll say a little bit about that later, because these things, electrons and neutrons, they do have EDMs in the standard model, but they're very, very, very low because they come in from like very higher order things like this, like CKM physics. Yeah, so only CKM physics, possibly, PMNS, the neutrino mixing matrix, and physics beyond the standard model. So for the electron EDM, for example, is generically sensitive to particles and forces that violate CP. And were there any other questions before I move on from this?
That's the only one.
All right. So I'll talk mostly about the electron, just because that's the simplest EDM to talk about, both theoretically and experimentally, but most of what I say is easily translatable to these other moments, which I will also talk about. So the electron EDM, because it can't arise from regular physics, with the exception of CKM, which I'll talk about. That means that you are sensing, you're not just looking, this isn't QED effects you're looking for some new particle with a CP-violating coupling to the electron, possibly at higher loop order. And if you make a back of the envelope estimate, which I'll walk through on the next slide, so you don't have to take my word for it. If you assume that you have a coupling with a CP-violating phase to the electron, if you have something that couples the electron at one loop, then the current experimental limits tell you that the mass of this particle has to be larger than 10 to 50 TeV or so. So it's pretty high. And that's from the existing experimental limits. And for two loop, things that couple the electron in two loops, it's roughly like a half to 2 TeV or so. So pretty high energy scales. It's a quote unquote background free experiment because the standard model value is very small. It's many orders of magnitude smaller than the current limit. This is actually, it's smaller than that in fact, but it's many, many orders of magnitude below the experimental limit. So we, maybe we'll get there in our lifetimes, maybe not. But because of this generic sensitivity to new CP violating physics, there's a lot of excitement that that you'd find something much larger than this value. In the standard model, this arises from the CKM matrix, so the CP violation from quarks interacting via the weak force. And the reason it's so small is because just to get CKM physics into something that couples with the electron in a symmetry violating way, you need at least 3 loops. Turns out all the 3 loop diagrams cancel, so you have to go to 4 loops in the standard model to get an electron EDM. So it's very, very small. This is a fairly generic argument. First, you can cook up specific models where this energy reach is even higher. Of course, you can cook up models where the energy reach is even lower. But in general, these experiments are probing fairly high energy scales. And here's that, oh yes.
Is there any easy way to see that all 3 loop diagrams cancel?
No. And this was the reason, so I don't understand any Feynman diagram calculations, if I'm being totally honest. But the reason I think it's actually non-trivial to see is because somebody basically wrote papers exploring, the third order, like basically calculating what the third order contributions were. And then later someone wrote a paper proving that they had to all cancel. So meaning like there were people who knew how to compute this stuff who didn't realize that they canceled. So maybe so I don't know if there's a really sort of elegant argument why all the 3 loop diagrams have to cancel. But I don't know, maybe someone else knows.
On top of my head,
Yeah.
I usually stop at 1, maybe 2. But
There we go, yeah. 3 is, 4 is too many, yeah. So this is that sort of 1 loop. This is for just a generic fermion. You can have 1 loop things like this. With 2 loops, you can get pretty generic things in these loops. So the mass reach at 2 loop is really probing some, things that don't necessarily couple directly to the electrons. You can probe a lot more things. But if you make an estimate for what's the size of the fermion EDM induced by these diagrams, you get something like this, which depends on, of course, there's like the charge, the fermion, but it depends on CP violating phase. You need a CP violating phase. That's why QED doesn't violate or make EDMs. There are no CP violating phases in QED. You get some coupling constant. You get a new physics mass scale. You possibly get some enhancement from flavor violation. It turns out if there's like charged lepton flavor violation, this number can go up, but you can also just assume it's like 1. And if you make some what theorists say would be reasonable estimates for these things, coupling constants, and just assume there isn't any weird flavor violation stuff going on, that's where you get this sort of 50 TeV-ish at 1 loop, 2 TeV-ish for 2 loop effects, given the current experimental limit on the electron EDM, which is this. Yes.
And that's a huge CP violating phase is 1.
Yes, that's an important thing I left out of here that I should fix. In fact, I should write myself notes because I'll probably find all sorts of errors in this. But yes, I'm assuming that the CP violating phase here is 1. So yeah, so importantly, these things are EDM searches are only sensitive to CP violating physics. If the physics doesn't violate CP, they would never show up, or well, practically. And I always like to point out and remind people that so the energy scales that these people who work in this field often talk about, like, oh, like these energy scales are like way higher than direct searches. which is true. They are way higher than direct searches for this particular thing. If you take a bigger picture, like say you come up with some supersymmetric model and you make some predictions for what the particle content would be, and then you say, what are the limits on the masses from the particles from my model? It turns out that the most sensitive limits for different members of your supersymmetric family come from all different types of experiments. They come from, in some cases, they come from EDM experiments, and they're really high. But in some, they also come from things like the LHC or from flavor violation searches. So I encourage you not to think of all these different things as like competing with each other, but they're all looking for different things and they're all good at doing different things. So like, hooray, let's all work together. So I'm now going to that sort of ends the kind of theory background motivation part before I start talking about more experimental stuff. But are there any questions? So here's if you want to look for an EDM now, after this introduction, you all want to look for EDMs now. Let's look for EDMs. It's very exciting. So how do you do it? You can do a very simple sort of idealized experiment on paper, PowerPoint, which is take your particle, your electron or whatever, neutron, polarize the spin so that it's perpendicular to some electromagnetic fields. And those fields, the dipoles will interact with the fields, the electric and the magnetic dipole. If you wait some time, tau, the spin will precess by some phase angle that comes from the magnetic and electric precession. And then you do it again. You flip, for example, the electric field. You do the experiment again. Now the phase that accumulates will be slightly different because the electric precession will be in the opposite direction now. And so if you take a difference of these two phase angles, you get something that's proportional to what you want to measure, the EDM, and then some things that you know about the experiment, like the field and how long it was precessing. So great, that's all you have to do. And this experiment is perhaps most closely realized. Yes?
So is there any reason that you still have a magnetic field? Like you change your electric field, but like is there any reason that you still have magnetic field on?
Yeah, great question. So why is there a magnetic field here? In principle, you don't need it. In reality, that magnetic field is always there. You can't get rid of it, no matter what you do. So if you can't get rid of it, you may as well try to control it and understand it and apply a very well-known field rather than be stuck with some field due to some, nuclear paramagnetism of copper something or other. I'll talk about that later though, because how do you disentangle, like for example, as we'll see, this is many orders of magnitude bigger than this. So like, how do you actually disentangle these given that you're looking for something very tiny on top of something big? So what do you do with the magnetic fields is a very good question and one that we will return to. So this idealized experiment is most closely realized in neutron EDM searches, because like neutrons, you can just they can just bounce around in a box or in a trap or something, which is really cool. And you can just like apply fields to them and see if they precess. And this was the first EDM searches were performed with neutrons, using neutron beams a long time ago. It says 49, but I think that should be 59. The current limit is, many orders of magnitude smaller than this earlier limit. And as Mariana mentioned, if you turn this into, so this, these unitful quantities like electron charge centimeters is the customary unit for EDMs because it's like a charge times a distance. And that can be hard to interpret. So we always try to reinterpret it as some more physically meaningful thing. And like Mariana said, you can turn this into a limit on the theta QCD, like the strong CP violating parameter as being less than like 10 to the minus 10. So that seems really small. Tomorrow you'll hear about axions, which maybe not from me, from Mariana, how to address this. And there are a lot of experiments that sort of measure EDMs directly, like directly of neutrons or protons or nuclei. but I won't talk about those. I'm going to talk more about like atoms and molecules. The sensitivity for that idealized experiment is, well, you're measuring a phase. This is the sort of observable that you're measuring, a phase angle of precession after some time tau. If you do repeated measurements, which you always want to do when you're looking for something small, this is what your sensitivity is for the EDM. It's inversely proportional to the field applied, the coherence time, and the square root of the total number of measurements. And so you want to make all these large, so your resolution is small, your sensitivity is small. So you want big fields, long evolution times, many measurements, and so this is somewhere where atoms and molecules have some nice advantages, why people work with them. The internal electromagnetic environment inside atoms and molecules is very extreme. So in quotation marks, you get very large internal fields. But also with modern coherent quantum control methods, you have the possibility to access very, very long coherence times and very large numbers. And also, one of the reasons I'm really excited about the field is because in the sort of foreseeable future, meaning in the next like couple of decades, these experiments will very likely improve their energy sensitivity by several orders of magnitude. Because a lot of this modern quantum stuff, actually none of the modern quantum stuff has basically not yet been implemented in these experiments, but it's like this close. So that's exciting. So we'll start with this one, the internal fields. Any questions so far? So the internal field idea is pretty simple. There are a lot of complexities that I'm actually going to spend some time addressing. But the basic idea is that the electric field inside molecules or atoms, I usually draw atoms, even though I mostly talk about molecules because atoms are simpler to draw. So if you say you have some valence electron in an atom, you know, atoms are like made of electrons, you could ask how, and other things, what's the field experienced by that electron? If you do a back of the envelope estimate, you'd find something like gigavolts per centimeter. If that unit full quantity doesn't mean anything to you, what you should compare that to is the largest electric field you can create over like macroscopic volumes in the lab by putting voltages on plates is around like 100 kilovolts per centimeter. So this is, you know, orders of magnitude larger than that. You know, and so, you know, so here's an example of some very high electric field electrodes that were created for an EDM experiment that I'll talk about later, the radium EDM experiment, and they can get up to like 500 kilovolt per centimeter in here, but that's, you know, it's really hard. And at some point you're limited by field ionization, just the fact that these electrodes are made out of materials which have electrons in them, and eventually the electrons will be just ripped out of the material. So you can't realistically come up with ways to push this up by, you know, 5 orders of magnitude or something. But in here you get that enhancement sort of for free. It's not really for, nothing's for free. And then the idea is, if say the electron or the nucleus or something has a permanent electric dipole moment, that causes a splitting in the energy levels. For example, if you have electron spin up versus electron spin down in this picture, those two states will split by something that's proportional to the EDM. And this is amplified by the internal field. The splitting is proportional to these internal fields. And since that splitting ultimately is sort of your observable, that means you get like a useful enhancement of these effects. This picture has several caveats, which normally, like in a research talk, like when I'm giving like a colloquium or something, I show this slide, but I skip over. I don't even talk about I don't even bring up the caveats because, like, who cares? They're really interesting, and I think they give you some insight into the physics that's going on and some motivation for why we do some of the things that we do. And so I'm gonna talk about them, which I'm excited about. So that's the basic idea. But before I talk about these caveats, I want to point out one really critical feature of these, like the only reason these experiments are practically doable is because these energy shifts are zero in the absence of time violating physics. So for example, in this picture here, these two states, the spin up and spin down state, are time reversals of each other. And so they can only be split in energy by some time reversal violating physics. And so it doesn't matter how complicated the atom is or the molecule is or whatever, no matter how complicated it is, these two states are exactly degenerate because they have like a symmetry protected degeneracy, except in the presence of the symmetry violating physics we're looking for. And that's the reason that's important. So in other words, these experiments are, I guess I said earlier, they were like theory background free. They're also in some sense like experimental background free, or they're standard model physics background free, but they're also like atomic and molecular physics background free in a sense. We're looking for something that's non-zero on top of something that should be exactly zero by symmetry. And so that's an important distinction from, for example, measure something and look for deviation approaches, like in G-factor measurements, because G-factors can be computed to very high precision. Molecular structure especially can't. Like the types of heavy molecules people use for these experiments, you can only calculate the structure on the like few percent level. And there's no foreseeable pathway to improving that by like 10 orders of magnitude that you'd need to resolve these tiny, tiny shifts. So that's not necessarily the case with atoms. Certain atoms, there are certain people, some of whom are in the room, who can calculate these sorts of things to extremely high precision, but for molecules, it's intractable. So that's good. We don't have to worry about the details of the structure. Of course, there's observation of, well, these up and down, spin up and spin down states are actually split by a magnetic field. So what do you, well, we'll come back to that later. But this is, in this idealized picture where there are no external fields, these things are exactly degenerate. So here's the first caveat to this internal field picture, this simple internal field picture. The electrons and the nucleus experience zero average field. Why is that? If you look, well, in this simple picture I drew, it's even classically, you can see why it has to be zero. The electron isn't actually sitting up there. It's, it's orbiting around, and its spin would average over, the dipole moment would average over the electric field, and it has, since there's no preferred direction of the electric field, the dipole interaction would have to average to zero. Again, this is true, even classically, this is true. This is always the case. It's basically, it boils down to the fact that the electric field is like a parity odd thing. And so if you look at anything that's a parity eigenstate, like molecular or atomic wave functions, you can sort of prove this is always true, since these eigenstates have well-defined parity. I'll say more about that later. But there's a solution, which is just polarize the species. If you apply an electric field, you'll again, even kind of classically, this picture sort of works. You'll pull the electron and the charged nuclei away from each other a little bit. So now you introduce some asymmetry in the field. And so now this won't average away anymore. So great, so this works. You can't do these things in free field, you have to do them in some applied external field. Okay, great. But so we'll talk about the physics of like, okay, how do you polarize an atom? Quantum mechanically a little bit, because it's it's interesting, but it's also it's a good vehicle to kind of review some basic quantum mechanics, but also it's a source of a lot of misconceptions. So atom and molecular wave functions, eigenstates, are always symmetric in zero field. Always, they're always parity eigenstates specifically. So something like an s orbital, obviously is symmetric. Something like a p orbital, you might think like, oh, that's asymmetric, but it's not. Because if you remember that you have to square this to figure out like where is the charge, the electron spending its time. Once you square this, these two lobes are identical. The electron has no sort of preferred direction where it's spending more time. However, if you mix these two states, for example, with an electric field, you can end up with wave functions that look like this that are lopsided. Now, something like this does have an asymmetry. This would have a dipole moment because the charge is spending more time up here than down here. And I'll say a little bit more detail about this on the next few slides, but in order to mix two states with some perturbation, you have to apply a perturbation large enough to overcome the energy splitting between them. So therefore, these things are an induced dipole. Right? This state, they don't have permanent dipole moments, but if you apply an electric field, the electric field induces a dipole moment by mixing them, and then that dipole moment interacts with the field. And this is, this statement has gotten me in the most arguments after colloquia than any other statement I make, but it's true. It's true. I can, I'll fight you for it. Nothing has a permanent electric dipole moment, except in the presence of like CP violating physics that we're like looking for. So what I mean is that everything, like every molecule, every atom, everything that we know about, actually has an induced dipole, which is induced by a mechanism like this. So you apply a field to mix two states, you get an induced dipole and therefore a quadratic energy shift at low energies, low E fields, and then approaching a linear shift at higher E fields. Something with a permanent EDM would have a linear energy shift all the way down to 0 E field. But everything we've ever observed it actually rolls off, at low field. Yes.
Where are the chiral molecules lying there?
Chiral molecule, it depends on it depends on how it's chiral. But I'll say a little bit more about this later. Usually, some molecules, especially like big floppy molecules that have very low symmetry, this transition point where it goes from being quadratic to linear happens at such a small field that just most people don't care. Especially people working at like room temperatures and solutions and stuff don't care because the field's so much larger than that. So this could be like for ammonia, for example, or for ammonia, for example, this is like the energy splitting is like a few gigahertz. And so with reasonable lab fields, you can polarize it very fully. So I don't think the chirality necessarily impacts this directly. But it's usually just that in order to be chiral, it has to have very low symmetry, and things with low symmetry tend to have like a forest of states that you can very easily mix.
But the state is the same, no permanent EDM.
Yeah, no permanent EDM, except in the absence of CP violating physics. Yeah, absolutely nothing. So here's a way to think about this. In some detail, apart from just hand waving. If you say consider a system with just a two-level system, an excited state and a ground state that are split by some energy. The Hamiltonian and applied field is given by this. All I'm doing is writing out these matrix elements and then as a matrix. The diagonal is 0 because these two states have the same parity, so they're not mixed by a parity odd operator. So the electric field has the perturbation from the electric field has no on-diagonal elements. And then I've defined D as this matrix element, basically. What's the coupling between the ground and excited state by the electric dipole operator? So you get some simple, off-diagonal matrix. Sorry that things like E and D appear several times in different contexts. This is the sort of standard conventions. You have to infer from the context whether E is like an excited state or a charge or something. So in general, these states E and G, in order to be mixed by an electric field, they can't have the same parity. They have to be opposite parity states. Otherwise, this product of their wave function would be an even function if they have the same parity, if they're both even or both odd, and therefore this matrix element, which you can think of as an integral, would be an integral over an even function times an odd function, which would be 0. So that's the sort of simple mathematical proof of that statement I made that you can't you can't couple things of the same parity with a parity odd operator. So the Hamiltonian of this two-level system is this. So this is just the energy splitting now on the diagonal, and then the off diagonal is this coupling from the E field. And this is it's a 2x2 matrix, so we can just diagonalize it exactly, and we'll actually get some good intuition by going. Or I hope that we'll get some good intuition by going through this exercise. So take this Hamiltonian, diagonalize it. Here's the answer for the energies, at least. Plus or minus, it looks like this, where I've defined this quantity eta, which is the ratio of basically these off-diagonal to the on-diagonal matrix elements. So the magnitude of this interaction divided by the energy splittings. And then you can plot some limiting cases. You can consider some limiting cases. In the high field limit, where the interaction is much larger than the energy splitting, you get things that just look like linear shifts, that look basically like, d times e, plus or minus d times e, whether it's going up or down. The eigenstates are full mixtures of, they're fully mixed, that should be a plus or minus there, e plus or minus g. So the eigenstates are fully mixed, even and odd combinations of the ground and excited state. And they look like this. This is the sort of the way you usually think of a dipole. It's like, well, the dipole is up or the dipole is down. So in this limit, that's what they look like. Those are the eigenstates, to good approximation. So we'd say this is the fully polarized or fully mixed limit. The other limit, the low field limit, is the one where maybe it's a little more confusing. So in the low field limit, you have quadratic shifts, indicative of an induced dipole, where you have a dipole moment proportional to the E field that then interacts with the E field. The eigenstates are, well, they're just E and G, the ground and excited states. But those are mixtures of these fully polarized mixed eigenstates. So in other words, down here at zero field, the eigenstates look like this. They're superpositions of these polarized up and polarized down states. And that always has to be true because these polarized states are not parity eigenstates. And in zero field, when your eigenstates have to be parity eigenstates due to the symmetry of the Hamiltonian, they have to be in these superpositions. So this picture of like, like a molecule with a dipole pointing in some direction, that's valid in a high field, but in low field, that's not the actual physical eigenstate. It's these superpositions. And so in order to start transitioning from low field to high field, that occurs where this parameter eta is about 1, which means that this interaction and the energy splitting are about the same. We commonly define what's called the polarization, which is basically what fraction of the eigenstates are these fully mixed eigenstates. It's 0 at zero field, it asymptotically goes to 1 at infinite field. And this quantity is going to pop up later, this polarization. But any questions about this? So that's the reason that's important, is because the EDM shifts are proportional to the polarization. This quantity P that I defined on the last slide. And the reason that you can see why that might be reasonable is because if you look in this fully polarized limit where like the dipole is up or the dipole is down, that means the internal electric field is sort of fully up or fully down. And so if you have some electron spin, which is interacting with that, the electron spin, by the way, you can have pointing one way or the other, because that's a spin. It's not a parity odd thing. So an electron can be pointing spin up or spin down in the lab, no problem. You can align these in the lab with a magnetic field, even if they're like in a molecule. So something like this, you get maximal EDM shifts. But in the unpolarized case, as we just saw, you have to be in a limit where you're in a superposition of dipole up and dipole down. But that means if you have some EDM interaction, it'll cancel out because this internal field will, on average, not point in any well-defined direction. So the EDM shifts are proportional to this polarization quantity, which you can also interpret as the projection of the internuclear axis on the lab frame. Any questions about this? So this is the reason why I talk about this is because this is the reason why atoms and molecules are so distinct for these types of searches. The internal field in an atom molecule, it turns out it's about the same, but you can't polarize an atom. In atoms, the opposite parity states are electronic excitations, which are EV-ish. They're high energy. Well, for me, EV is like super duper high energy, and that means if you run through some approximate numbers, you can get sort of part per thousand polarization, even at these sort of like maximal fields. But molecules, because they have a ladder of rotational states of opposite parity, which we'll talk more about later, sometimes they're even smaller. The energy splitting between opposite parity states is at least 1,000 times smaller. And so that means you can get order unity polarization even in like 10 kilovolts per centimeter. So like 10 times smaller than the maximum field, which, this field is not that hard to make in the lab. And so molecules, I put it in quotation marks, molecules are 1,000 times more sensitive than atoms to EDMs, not because they're intrinsically more sensitive, but because you can actually polarize them in the lab frame, whereas you cannot do that with atoms. So then there's a question I get asked a lot, which I decided to make a slide for, which hopefully isn't too much of an aside. A question that I get asked a lot is like, what if these opposite parity states have no energy splitting? Like, what if you have exactly degenerate states of opposite parity? Like, is that a problem? Like, is that a CP violation or something? There are a few ways to answer that. So for example, this is the Hamiltonian for the n equals 2 states in hydrogen, NLM in an electric field, according to Shankar, which is like my go-to quantum mechanics book. That wouldn't necessarily be any symmetry violation, right? The symmetry violating aspect of EDM searches is not the fact that it's a permanent dipole moment, it's that it's a permanent dipole moment that has to be aligned along spin. That's the part that is a symmetry violation. So you could have a composite object like a hydrogen, like an atom, like hydrogen atom, that just sort of coincidentally had degenerate states of opposite parity. That wouldn't be a symmetry violation. It wouldn't force this alignment of parity even and odd things. Of course, I would argue that these probably don't exist in nature. It's hard to get things that are exactly accidentally degenerate without some symmetry or hidden symmetry or something. So there probably aren't any examples of this. The hydrogen atom is not an example of this, right? Like these two states in hydrogen are actually split by a really tiny amount. The 2s and 2p states in hydrogen are split by the Lamb shift, which is like micro EVs. So it's really small, but it's not zero. But it's much smaller than everything else. So it's just like, who cares? It's just a zero, whatever. For this, for this treatment. So the n equals 2 states are split by the Lamb shift. Even things like chemistry textbooks commonly talk about ammonia or water having permanent electrodipole moments. Those are also split. Their opposite parities are split by something else that's really tiny. So it's always non-zero. So usually when people say it's zero, they just mean it's like it's really small. So like, who cares? So that's the end of what I'm going to say about polarization. Any questions about polarization? So the other sort of simple, this simple internal field picture has another caveat, which is going to actually lead us to some kind of interesting physics discussions, I hope. The second picture is that even when you polarize them, the electrons in the nuclei still have to experience zero average field. And that's something called Schiff's theorem. And you can prove it sort of like, using math and stuff. But the basic idea is that because atoms do not accelerate in static electric fields, which is an empirical fact, the average force on everything in the atom, which is electrostatic and therefore is proportional to the average electric field on everything in the atom, has to be zero in steady state. So, or in other words, charged particles, you apply a field on them, they just move to the point where they on average experience zero field. That's how ion traps work. You make a rotating electric field where there's some average zero in the middle. Ions always push to the middle. So, this is true, by the way. And there's no way around it. But there are some sort of sneaky evasions of this, which this isn't it's not some lab trick that you do. It's more just like, it turns out there are like intrinsic evasions of this. Electrons move relativistically and nuclei have complex shape. Those are the ways that these are evaded. So the relativistic electron motion idea is that the dipole moment is a vector, it experiences a Lorentz contraction. And so there's a correlation of velocity, because there's a correlation of velocity and position relative to the nucleus. Again, even classically, that's true. This dipole moment D, say of the electron, is not a constant in the atom, right? Because it's Lorentz contracting. So even though the electric field may average to zero, D dot E will not average to zero because D is not a constant. So you can't just pull it out of the expectation value. And an important consequence of this observation is that this is most sensitive very near the nucleus, where the Lorentz contraction is the largest because the velocity of the electron is largest. And so this effect depends on very short range electronic wave function details near the nucleus. And if you want to ask, like, well, how fast do we have to worry about relativity? how fast is an electron? You can make a back of the envelope estimate. For Z protons, the orbital size is basically the Bohr radius, which is 53 picometers divided by the nuclear charge. And then if you make some like sort of de Broglie estimate for what the velocity is, the momentum is, you find that it's roughly the proton number times the fine structure constant times the speed of light. So even for fairly light atoms, this is non-negligible. So these relativistic effects, and for heavy atoms, they're like order unity. So this relativistic motion is what allows you to actually observe the electron EDM. That's also why you need very heavy systems for these, which we'll talk about more later. So the electron experiences what's called an effective field. So you get some effective Hamiltonian where it's some average EDM dotted with some effective field. So basically, once you take into account averaging over this Lorentz contraction, so the average internal field is 0, but the average effective electric field is non-zero. And this is because you require this short-range nuclear penetration of the wave function. This is only non-negligible for core penetrating electrons, so those that have S or P character. If you may recall from the fact that we've all memorized the full solution for the hydrogen atom in terms of all the associated Laguerre polynomials and stuff, the wave function, the radial part of a wave function, a hydrogenic wave function, goes like r to the L for small r. So when L equals 0 or 1, you get some density near the nucleus, but it falls off pretty quickly for D and F and higher orbitals. As a side note, for the electron EDM to be observable, they can't be paired off as a singlet. So if you take an atom where you have a sort of spin up, spin down pairing of electrons, the EDMs will sort of cancel out as well. Because this is a relativistic effect, you can make some estimate for the scaling, and it scales, this effective field scales roughly as z to the cubed, at least for things in the same column of the periodic table that have this sort of similar electronic structure. And so if you do like some calculation and you plot, for different metal OH molecules going down the periodic table, in some units, these effective fields actually, are pretty, on a log plot, are pretty well described by lines. So these power law, this ZQ power law is like pretty good. Again, for chemically similar things, same column of the periodic table. If you want to calculate these things, you have to use very advanced relativistic quantum chemistry. Which is challenging, but these days is good to a few percent. There's coincidentally, there's a talk. I didn't know this until I already made this slide, but that person is like here visiting, giving a talk tomorrow. So if you're interested in learning more about this, see Robert Berger's talk tomorrow afternoon. And by the way, this effective field is not an observable, so you can never compare it with experiment. What you can do is calibrate hyperfine structure. So electron spin, nuclear spin interactions in an atom or molecule, which you can very easily observe. It turns out you basically calculate those the same way. So you can kind of benchmark your calculations like that. So that's how electrons evade Schiff's theorem. But what about nuclei? The nuclear motion is definitely not relativistic. So you may be concerned, are nuclear EDMs unobservable? There's no Lorentz contraction for the nucleus in an atom, practically. So here's the other sneaky evasion of that, which is that only the charged part of the nucleus obeys Schiff's theorem, and not the entire nucleus isn't charged, because the nucleus is made of protons, but also neutrons. And both the protons and the neutrons could have an EDM, even though the protons on average must experience zero electric field, the neutrons don't. So if there's some non-overlap of charge distribution and mass distribution, for example, if all these nucleons have an EDM, you'd get some sort of net nuclear EDM. And if these two things don't overlap exactly, which they generally won't, you can get what's called a nuclear shift moment, which depends on this mismatch between charge and mass in a nucleus. It can be significantly enhanced in highly deformed nuclei, which I'll say a little bit more about later. If the nucleus isn't a sphere, but if it's just some messy shape, then this non-overlap can be pretty big. And so to understand why, how does this give rise to something sort of observable? You can notice that this nuclear shift moment, it looks like a charged shell with a dipole-like distribution. That means that it effectively leads to an electric field inside the nucleus, E sub NSM, so some localized electric field in the nucleus, which is correlated with the nuclear spin. Because the dipole moment distribution giving rise to this charge distribution comes from the EDM of the nucleons, which have to be correlated with the nuclear spin. So you get effectively an electric field correlated with the nuclear spin that by itself violates, T and P and all these things. And if you have an atom or molecule where you have a lot of electronic wave function penetrating the nucleus, this electric field will mix the opposite parity orbitals in the atom or molecule, as we've seen, and it will lead to an induced atomic or molecular EDM. So you again, like the electron, you need S or P orbitals, just like the EDM, but for sort of totally different reasons. Because they actually, in this case, it's because they have to actually sample this internal field in the nucleus. Here, though, yes.
Now thinking about this, we always assume that, for example, for the QED effect, for the same reason that we wouldn't have effect except S of the orbitals. But theoretically, we know it's not true. The reason being because, and I mean, this is just kind of something occurred to me, because the way it works, that now you have some effects which affect us at the orbital, so that affects all the orbitals. So what it does, it affects the self-consistent potential. So essentially, why there is no direct effect on the orbitals, there is an effect on the other orbital, because now potential of all the other electrons change. So we actually see significant effects on the F orbitals due to the QED. Which you assume there is no effect on F orbitals. This I was kind of, it never occurred to me before. I just kind of wonder something like this, say in principle, could induce effects on things which are not S and P, because there is exactly the same logic for both isotope shifts. For isotope shifts, again, you see F orbitals isotope shifts, not because they're all around the nuclear, but because the shift, the interaction changes all the other orbitals and they essentially bound. So essentially what it does, it contracts, it's a meaning field. And that affects all the other fields. And they actually find this is not unusual. Of course, you always probably have a larger effect, but maybe if you have like a great molecule, but there's no I don't know what to say or not.
No, that's a good question, and I'd never thought of that. Yes, the basic idea, if I understand it, is that okay, you need S's or P's to come in here and mix, but if that's even if you have sort of like filled S and P orbitals or something that maybe aren't valence, if they touch this, they will change their shape, which will then change the shape of the other orbitals. And
it's not really not a small effect.
Yeah, and I don't know if anybody's ever calculated that.
I'm just curious.
Yeah, it could be interesting. If that's true, it would open up a lot of interesting regions of the periodic table for these searches. Yeah. In this case, you don't need unpaired electrons. You just need electron density at the nucleus. So you can use something with paired off electron spins, or in other words, a diamagnetic atom or molecule, which people often use simply because when there's no electron spin, you get like simpler structure and you get less magnetic field sensitivity. Since this is some moment correlated with a nuclear spin, you need a nuclear spin for this to be observable. So you have to have a spin of at least a half to define this vector quantity. And then you get a Hamiltonian. I'll say a little bit more about this later, but you get a Hamiltonian, which basically looks like external electric field dotted with the nuclear spin. That's your sort of observable. So it's very much like the electron EDM picture. You're looking for some energy splitting between spin up and spin down, except now it's nuclear spin up and down. But the way the experiments proceed is very, very similar. And these moments are actually significantly enhanced when you have non-spherical nuclei, which it turns out is a thing, surprisingly. If you take the sort of surface of a nucleus and you decompose its shape in terms of spherical harmonics, you can have quadrupole deformed nuclei where it's sort of stretched out in one direction. But you can also have octopole deformed nuclei, which is the next order in the spherical harmonics, where you actually have something like this, where it's like a pear shape, or since I'm live in California, an avocado shape. When you have this, you get significant enhancements in this nuclear shift moment, largely because the shape is so big and messy that this non-overlap of things, it becomes very large. It's not a difference between two things that are about the same. This is a challenge because these types of species, it turns out, are hard to come by. Heavy, spinful, deformed nuclei are short-lived. That's how it is, it turns out. So it's basically like actinide. So they're all radioactive. Can still work with them. But the reason that a lot of people are excited about these is because this factor of 100 to 1,000 or so in like nuclear sensitivity enhancement is on top of the molecular enhancement. So if you say take a molecule with a deformed nucleus like radium, it's around 1 million times more intrinsically sensitive than say atomic experiments with spherical nuclei like mercury or xenon. Which are mercury, by the way, is the most sensitive nuclear CP violation moment experiment. These experiments are highly advanced. They're super hard to beat. That's why the limits still come from these. But also, as I'll say more later, because these nuclear symmetry violation experiments especially are sensitive to many different sources, you actually need experiments in different species to like nail down the physics. And some very exotic nuclei might actually be another factor of 100 to 1,000. So protactinium-229 containing molecules might be 1 billion times more sensitive, but turns out that depends on some as of yet unproven nuclear physics stuff. I'm gonna skip over this part about why octopole deformations in particular. You can look at the slides and ask me later, but basically it's a combination of the fact that they have a big messy shape and the fact that they have a rotational structure in their nuclear energy levels. They have opposite parity states of low energy and a big messy shape that makes them very intrinsically sensitive to these shift moments. Another way to evade Schiff's theorem is to just use magnetic effects. So a magnetic quadrupole moment, which would be a quadrupole moment sort of whose orientation is determined by a spin, would also violate CP, kind of for the same reasons as the other thing. It requires some correlation between pure angular momentum and something with a spatial degree of freedom. So magnetic quadrupole moments intrinsically violate all these same symmetries. But now they exist in nuclei, right? Because there aren't, fundamental spin 1 fermions. So you can't have like a particle with an MQM, but you can have like a nucleus with an MQM. And a way to think about how this can arise from CP violating physics, if you think of a nucleus with a valence nucleon that has an EDM, that EDM, as it orbits around the nuclear spin, an orbiting EDM creates an MQM. So that's how you can get MQMs in a nucleus. And that's the sort of connection to observing symmetry violating effects in the nucleus. So this creates a magnetic quadrupole moment sort of correlated with the nuclear spin. And in an atom or molecule, this magnetic moment interacts with the magnetic field basically created by an electron to give us symmetry violating energy shift. In this case, you need a nuclear spin of at least 1. You need a spin of 1 or higher to even define a quadrupole moment. Similarly, there are enhancements due to nuclear deformation. In this case, all you need is a quadrupole deformation, which it turns out is fairly common. When you have a quadrupole deformed nucleus, this sort of single orbiting nucleon picture breaks down in a good way, meaning that you have effectively a bunch of nucleons orbiting around, contributing to the MQM. So inner shell nuclei, even if they're paired off in their spin, will still contribute to this MQM with something that's typically around an order of magnitude or so enhancement. So it's not as dramatic as the octopole enhancement, but it's factor 10 is pretty exciting for experimentalists. And again, the experimental approach is similar, and I'll show a slide comparing and summarizing these, but it's the same idea. You reorient these spins, the electron and nuclear spins, and you look for some symmetry violating energy interaction. So for EDM, for electron EDM, you get a big enhancement just from the large field, either in an atom or a molecule. This enhancement here is, say, over the field you can create in a lab. You get about 1,000 times larger in an atom, or about 1,000,000 times larger in a molecule. So this gives you a big enhancement in EDM sensitivity. For MQMs and EDM, and that should be NSM, nuclear shift moment. You, in addition to that field in sort of internal electromagnetic enhancement, you also get these nuclear effects that give you another factor of 10 to 1,000, or even 1,000,000. So you can get like very large amplifications of these effects of symmetry violation by putting the things in an atom or molecule. Yes.
Is that the right statement that technically it would be about the same difficulty, technique MQM and EDM on the same molecule, or that would not be a right statement to say?
That is not the right statement to say. I think on actually I'll skip to this slide. Actually, no, yeah, before I skip to this slide, yeah. So I had said that ground state quadrupole deformed nuclei. This is the sort of chart of nuclei, the neutron number, proton number. Things with large beta 2, that's the parameter quantifying the quadrupole one. These are very common. They're kind of everywhere, but these octupole ones are pretty hard to find. So what is it, just as a recap of like, what do these experiments look like? What are they looking for these different observables? They're very, very similar. So for an EDM, you're looking for an electron spin up or down interacting with an internal field. For a nuclear shift moment, it's the same thing, except it's the nuclear spin now. For an MQM, it's basically the same thing, except there's an additional level of complexity, which is that you have to have an unpaired spin for an observable MQM in an atom or molecule, because the magnetic field that the nucleus senses actually comes from the spin of the electron. So you need an electron spin and a nuclear spin. And then the idea is you look for relative splittings as you reorient these two spins relative to each other. You'll change the sign of like your EDM shift or your MQM shift. So you have to basically do more measurements and then reconstruct what each of them is. So like in principle, the experiments are basically the same. You just do an EDM experiment, but in something with like multiple levels. But in principle, it's a lot harder because you have to have, so for EDM experiments, they always use something with no nuclear spin. So the structure is just so much simpler. For MQM, you have to use something with both a nuclear spin and an electron spin. And when they're on the same atom, that just means that the structure is very complicated, especially in a molecule. So you just have to work with more complex species. But the idea is exactly the same.
Let me just reiterate my question. If you are measuring electron EDM and MQM with fermium OH, would it be about the same difficulty of seeing the effect?
Yeah, if you're using this, yes, right. So if you're using the same, if you're using say 173 ytterbium OH, which we use in my lab, yeah, I think you can't get one without getting the other. So meaning that like you're kind of measuring, you have to measure them both at the same time in a sense.
Okay.
So you kind of get them both for free. But if you just wanted the electron EDM, you'd work with a different isotope with no nuclear spin, and just everything about it would be simpler.
Okay.
Yeah, exactly,
Yeah.
exactly.
Okay.
Yeah.
Just one. Okay, that's a different.
Exactly. Yeah.
Okay.
So electron EDM experiments gravitate towards things with no nuclear spin just because the structure is so much easier. And for this reason, because these things are all very similar in how they look, people usually just call these things like EDM experiments, even if you're looking for a nuclear shift moment, which is not an EDM. It's just like it's an EDM experiment. And as a reminder, all of these shifts are proportional to the polarization. So we only walk through the polarization argument with the EDM, but it's true for all of them. The shifts are proportional to the polarization. So you want to work with a species that's as polarized as possible. Any questions about this? The reason people are interested in looking for all these different things is because there are many different sources of CP violation in an atom or molecule. So if you look at just the electron, you can look for, say, the electron EDM or some CP violating electron nucleon interaction. In the nucleus, you have access to completely different stuff. You have like hadronic versus leptonic CP violations. So quark EDMs, sort of strong force EDMs, nucleon EDMs, new symmetry violating nuclear forces. And all of these experiments probe, different aspects of this. So that's why there's interest in taking this kind of broad approach. Specifically, if you write some like effective field theory and you sort of parameterize like what are the different sources of CP violation. So like permanent EDMs or CP violating gluon interactions, et cetera. There are like 13 different parameters. And so if you measure one thing in one species, you can't get information about 13 parameters at the same time. You actually have to search for multiple, you have to do these experiments in multiple species with different relative sensitivities to these different effects. So for example, for electron EDM experiments are actually sensitive to two things. They're sensitive to the electron EDM, but also to C sub S, which is I drew it earlier, it's basically a symmetry violating force between electrons and nuclei. And it turns out that in these experiments, those are indistinguishable. If you measured some non-zero signal, you wouldn't actually know what it was coming from, because the energy shifts are actually some linear sum of those two effects. But if you have two experiments in two different systems with different relative sensitivities, which every atom molecule will have different relative sensitivities to these two effects, then you can make exclusion plots like this, where each experiment maps out a band in like EDM versus scalar pseudoscalar interaction parameter space, and so you can get sort of robust limits on these things. Or in the eventually when one of these things is measured, if you want to actually say what is it coming from, you have to do it in multiple species. So that's another reason why people are pursuing these different approaches at the same time. Another thing where we need lots of like sort of input from all different places is, so ultimately, like as an experimentalist, I measure energy shifts. That's what we want to do in the lab, measure symmetry violating energy shifts. But ultimately, we want to be able to say something exciting about like supersymmetry or something. So how do you go from here to here? It turns out there are several steps. So first, you need atomic and molecular theory to calculate sensitivity parameters, like how sensitive is your atom or molecule to like the electron EDM or to like some nuclear moment. And for things with nuclear, when you're looking at nuclear moments, there's an additional level of complication, which is you need nuclear QCD theory to connect these sort of collective things to underlying observables, fundamental parameters like interaction coefficients or quark EDMs or something. And then you need high energy theorists to connect these fundamental parameters to some like new beyond the standard model theory. So there's a very wide range of theory that supports this type of research. So this, I'm not going to go over this table. I include it for your reference as a summary of like, for these different types of experiments, what are the features you either want or need or don't need, and why is that? So you can, if you're bored, you can print out a blank version of this and try to see how many you can fill in. If anyone gets it all right, you get a free coffee. So now I'm going to transition to talking about more experiment focused stuff. It seems like a good stopping point to ask if there are any questions.